It is my pleasure to be here in Manchester and to actually be giving this presentation to the broader BP-ICAM. So today what I'm going to be talking about are extreme environments and dynamic morphology. And so often when we think about extreme environments, we think about them as places for failure and degradation. But what I want to talk a little bit about is how we can anticipate and understand some of the evolution that happens in these environments and use it to our advantage. Okay, so when we talk about extreme environments, we can be quite creative in the sorts of examples that we think about. We can think about things relevant to the ICAM in terms of oil and gas refinement. There are plenty of extreme sort of environments there, but we also can think about other places with nuclear power generation, seafaring, other forms of power generation. Many of these different applications have the complexities of high temperatures, high pressures, chemically aggressive environments, and quite frankly, there are few materials that can survive these conditions all by themselves, and often we rely on material systems to tackle these challenges. Now, I want to reiterate the fact that in these conditions, we have these commonalities of temperature, pressure, and aggressive environments, right? And if we, and this slide really betrays my training as a material scientist, is that this is the materials tetrahedron, and we're looking at the concepts and how these ideas are related between the properties of the material, the structure of the material, and the processing of the material. Now, in particular, this processing here, when we think about using processing to manipulate structure to change the properties, we are using things like temperature, pressure, and chemically aggressive environments, right? We are intentionally using the same sorts of variables that we use to define the extreme environments that I gave those examples of before. And so what I would challenge you to think about is that these sorts of high temperatures, high pressures, high loads, cyclic sort of loading, or chemically aggressive environments may actually, if we use them correctly, could be used to our advantage. Rather than putting the material into service in its optimal conditions, we can think about using and knowing what the service conditions will do to further enhance the properties rather than just thinking about it as a degradation mode. So this is kind of how we approach, generally speaking, a lot of the problems that we address in my particular group. And this means if we want to use these service environments, we really have to understand at a mechanistic level the evolution pathways associated with the combination of variables that we're interested in here. And so this means that not only do we understand the endpoint, the thermodynamic equilibrium of a system, but that we understand the path by which it gets to this thermodynamic equilibrium, and often that pathway is influenced by the morphology of the material itself. And so there's a lot of interplay here, and all of those factors will ultimately influence the durability and the degradation and or change of properties in these sorts of extreme environments. Okay, so just to give you a brief idea, since I don't know necessarily all of you here, and I certainly don't know everyone who's on this particular call, the types of problems that we're working on both within the ICAM and without, all of them have the common themes of using non-equilibrium processing methods, advanced microscopy, and in many cases small-scale mechanical characterization approaches where we can do site-specific probes to correlate things as we go along rather than testing big, large specimens that are difficult for us to expose to these sorts of environments. And in this particular case, what I won't get to talk about today are kind of these top two up here. I'll work on structural ceramics, where we're looking at the collective deformation, the plastic deformation of polycrystalline ceramic materials, and radiation tolerance of such ceramic materials, where we're looking to, again, use the combined effects of large thermal gradients and radiation damage to actually create a structure that's useful for us. What I will focus more on today are these two quadrants down here on the bottom. Our work on protective coatings is sponsored by the BP-ICAM, where we're looking at conditions of fouling, oxidation, corrosion, and so on and so forth. And this really actually feeds in quite nicely into some of our understanding of nanocrystalline metals and how we can use nanocrystalline metals to understand and develop new alloys for these sorts of environments. So we'll really focus on these two ideas throughout the course of this talk. But if you take nothing else away from this particular talk today, I hope that you appreciate at least our perspective that there is some potential in using the environment itself and understanding the evolving structure property relationships as a benefit rather than just as a degradation mechanism. I'd be remiss if I didn't properly acknowledge our funding for all of this work, the BP-ICAM obviously, but also funding from NSF and the Department of Energy. And then, of course, my fantastic graduate students you can see over here who work very hard on this. A lot of the work that you'll see today particularly is from Pralav Shetty, who is supported by the BP-ICAM, and Megan Amy here. Okay, so let's start with a specific example that is very relevant to this particular audience and thinking about what makes oil and gas a so-called extreme environment. Now we can see this is an example of a pipeline here. There are many other spaces within the oil and gas industry where we might consider extreme, but the examples you can see here involve the degradation of this pipeline either through corrosion or through buildup. Right? Both of these challenges are very expensive. They can cause safety issues, and so we would very much like to address them. And I think the dedication of many of the ICAM projects evolve around some of these problems. And the big challenge, one of the challenges aside from the temperature, are the actual materials that we're working with here. And so for our particular project, we were focused on these sorts of asphaltene-like molecules, an example of which you can see down here. And this is just one of the possible components of crude oil or other sorts of oil products, and they're very complex. This is just a simulated model. They're actually difficult to characterize as well as to understand how they're working, both interacting with each other, but also with these sorts of structural materials. And so ICAM 15 is designed around understanding this through kind of simplified means. All right, so the way to tackle this challenge, obviously ICAM 15 is one of the larger ICAM programs involving all of these universities here, obviously Manchester, Imperial, Cambridge, and ourselves at Illinois. And the goal of the overall project is to understand both the origin and the relationship of nucleation, aggregation, and deposition upon surfaces that eventually result in fouling and scaling. And so from this particular perspective, I'm talking about using the processing environment as an advantage. First, we need to understand the existing degradation mechanisms before we can get to that point. So that's kind of what we're doing here. And our approach is to take and focus on the latter part of this objective statement. Based on our background, we have, like I said, many other collaborators who have beautiful expertise in understanding interactions within the solution and so on and so forth. But we'll focus on interaction of these carbonaceous materials with the surface itself, and focusing on two distinct variables, both the chemistry of the surface to begin with and how it evolves, as well as the geometry or morphology of the surface and how that impacts or the deposition processes that we are beginning to elucidate through this program. Okay, so just to make sure that we're all on the same page, like I said, this is a very complicated problem, and so we want to simplify some things so we have a little bit more control over the system. And so in order to do this, we are working with both stochastic surfaces, so we're changing and manipulating the surface morphology through polishing. So you can see here we have some examples, a comparison of a relatively smooth surface versus one that has been intentionally roughened. So my poor students polish this and then they make it rough again. And then we also have these deterministic surfaces that are created by my collaborator Paul Braun and his student Wenyu Zhang. And in this particular case, we have a very well-defined length scale between these disparities on the surface. All right, and so in this case, these are very model surfaces. And here, the common steels, these are real steels that might be used in pipeline applications. So we're bridging some gaps. We have different levels of our assumptions. In terms of exploring the fouling behavior, we're working with model asphaltene molecules produced here at Manchester. This is one of them, which we'll refer to throughout this talk as A2. And there's some important properties about this particular molecule, particularly in that as we go to higher temperatures, it changes its structure. And I also would like to draw your attention here, in addition to these nice aromatic rings that we have on the end, we also have some sulfur molecules in there. And then in order to actually do this test, we put it in a little autoclave like this. You can see down here we've got little coupons of our metals. These can either be these sorts of deterministic structures, they can be pieces of our steel, and they sit kind of at a vertical angle so we don't have a lot of gravitational deposition during this process. But either way, we put in this model or this surrogate oil, we seal it up and we put it in our furnace. So that's what we're, our experimental approach. So what do we actually see? And we'll start by thinking about or working with the concepts of roughness or surface morphology first. And many of you might be familiar with the idea that within several areas of oil and gas, we intentionally make surfaces smooth, and we actually go through quite a lot of effort to improve the smoothness of the surface, because there's some experience that suggests that those smoother surfaces degrade or foul at a slower rate. And so we really wanted to understand what was kind of behind this. And so what I'm showing you here are some of our deterministic structures with different length scales. Okay, and so the smaller ones over here, they have these little plate-like deposits on them, and these plate-like deposits are about the same size as the voids that they are sitting on. As we go up and increase the length scale of our surface, the platelets also grow. And at the larger scale, we see even larger. So each of these they're all the same magnification, right? And it's quite interesting here. It suggests that whatever's happening in the solution in this particular case is further influenced by the surface morphology. So it's quite clear in this particular case at the smaller scale that the surface morphology somehow limits the relative growth. I'll show you a schematic on the next slide here. But I want to further suggest that we do see these sorts of plate-like structures on our carbon steels, right? So this isn't necessarily just an effect of our unique surfaces here, in terms of chemistry at least. But these plates are actually also a unique property of the model asphaltene molecule that we're working with, and that if we look at this DSC data here, we have this crystallization exotherm that happens just below our experimental temperature here, and we believe that that's why we see these plates, whereas we don't necessarily see this nice morphology at the lower temperatures if we do the same sorts of tests at room temperature. Now let's think about this a little bit more in terms of what could possibly be happening here and how the surface morphology might actually be interacting with these plate-like crystalline aggregates of our asphaltene molecules. And largely we believe this is a sort of a steric hindrance mechanism, wherein if you have deposition of a very small aggregate that might form in the solution and it interacts with the surface, it will continue to grow there until there is some sort of limitation, physical barrier on that. Now presumably, if you would fill in all of these holes, and once you have a continuous mat, this roughness doesn't matter, but this certainly influences the rate at which you would have continued buildup on our surfaces. Okay, so we can see that roughness at low temperatures, relatively low temperatures, kind of intermediate between room temperature and what we're going to define as high temperature, the roughness does play some sort of role. As we go to these higher temperatures, we no longer see this plate-like morphology, so these are the same three length scales in our deterministic structures that I showed you previously. And we don't see those plates anymore. We see more of a wetting behavior on the surface where we do see these deposits. And then on top of those filled-in holes, we start to see bigger clumps kind of coming out. And so what this suggests here is that the wettability, once the asphaltene starts to soften, is becoming important. Now I have to qualify a lot of this, especially these high temperature ones, with the fact that all of the surfaces that I've showed you so far have intentionally been passivated with atomic layer deposition layer of alumina or aluminum oxide. And we did this intentionally because we wanted to isolate the chemistry effects from the surface roughness effects. So the question is, what happens when we take that surface passivation, that layer of aluminum oxide, away? Well, this is what happens. So what I'm showing you here in the center, and I'll show you quite a few of these plots, so it helps to walk through it here, is I'm going to plot the roughness of the surface, and this is measured by surface profilometry, and it's a consistent measure that we do and repeat for all of our specimens, versus the mass gain. So once we have taken our specimens and put them in our autoclave and done our fouling, we weigh them before and after. And so that is a measure of the relative amount of fouling or deposition that we have on our specimens due to these interaction of the carbonaceous materials. And so what you can see here is that, sorry, I think I lost my labels, but this micrograph up here, it corresponds to this data point here labeled as A. This micrograph is a relatively smooth X65 steel. So it's a low, high strength, low alloy steel, often used in pipelines. And you can see this is no longer a smooth surface. After the fouling process, we have large depositions on the surface here. And you can see that measured as a measure of the mass gain. Right? And these are kind of smooth over here, and then these big mud cracks, and in between these islands, we have these globular structures. On the surfaces that started much rougher, so this micrograph corresponds to this data point here, much rougher, about 3 microns of average roughness, we have a very different morphology on the surface in these big, very large globular structures, which are in fact hollow. If we look elsewhere, we do see some sort of continuous deposits, but there are fewer. We see more of these sorts of deposits here. And so the mass gain on rougher surfaces is much higher. Right, so this kind of corroborates our earlier observations on the effect of roughness, and this gives us some interesting insight in looking at the morphology. We'll get into more of that on the next slide. But before we do that, I want to just give you some reference here is what happens if we put that aluminum back on the surface. And that corresponds to these data points down here. So these are still the same steel surface that we're working with in the top 2 data points, except obviously there's substantially less fouling. And if we actually look and go searching for deposits on these surfaces, I will forgive you if in B you can't see anything, it's just a gray box, because effectively it is a gray box. There's something on the surface, but not much. Over here on D, which corresponds to this rougher data point here, again, still very low mass gain. All the contrast you're seeing here is just from the intended initial roughness that we put into these surfaces. There are examples, and I'll show you them later. We do see some areas of deposition here. Obviously, we're measuring something, but we have to look very hard for them. Okay, so in this particular case, what we can see is that roughness is important unless you change the surface chemistry. All right, and so let's dig underneath. And so if we take one of these heavily fouled surfaces, in this particular case I'm showing you an example of the X65 that has been polished to a smooth finish. And so we have these big island-like deposits with all of the mud cracking, and in between there are these kind of globular sorts of regions. What we did is we zoomed into this little orange box here, and we did a fib cross-section there just to kind of get an idea of what's going on. Is this a continuous layer of carbon-based material? And what we see here is that these continuous areas, the big ones that we see over here, these are continuous mats of carbon-like material going on here. But underneath, and remember, we polished this particular sample to a smoothness of less than 100 nanometers of roughness. And so all of this, that wasn't there when we started, this is all deposit material as well, except it's not necessarily just carbon-based. If we look more carefully, for example, over here in this particular example, we see it's almost like a bubble. And inside of that bubble is a nice little cube, which is an iron sulfide. All right? And so if we look at our EDS mapping down here, this is just the secondary electron image, we can see that we do in fact have a lot of sulfur in the deposit, but more importantly, we also have iron in the deposit. So iron is being dissolved from the surface and reincorporated into these deposits, which strongly suggests that it's not just deposition that's happening here, we also have a corrosion mechanism that is active, and that corrosion mechanism actually may be accelerating and exacerbating the deposition process. All right, so basically what we're showing here, and I'm not going to go into all the details of this, but when we put the oxide on the surface, that effectively prevents the corrosion reaction from happening. So if we can stop the corrosion, we turn off much of the fouling behavior, especially at high temperatures. So the big question is whether or not we can create an oxide on a carbon steel in a reliable way, right? One, because not all oxides are created equally, right? Yes, low carbon steels will form an oxide under oxidizing conditions, but they're not necessarily oxides that are going to stop a corrosion reaction, right? That's why we have stainless steels, because regular carbon steel isn't necessarily going to do that. And I want to show you why not all oxides are equal. If we look at these, and in fairness, these are both steels as well. One of these is a, let's see, this one over here is a low carbon steel, and this one over here is at least a low stainless steel, and they both have been oxidized at very high temperatures. So this is quite extreme. It's not fair. They wouldn't really be used in the surface, but they're good examples. In the case over here, you can see what I'm showing you. This is actually what the scale looks like. So the iron, the steel alloy is down here, and all of this is oxide scale. And you can look at the color maps, and the color maps tell you, these color maps here tell you the different species, the chemistry, and the orientation of those different oxides. And the other big thing that you see, there's big cracks between the alloy and the scale that's forming on top of it, right? So clearly, The oxides that are forming in this case are not necessarily mechanically robust, they're not fully dense, and so because of that, they're never going to form a good corrosion barrier or diffusion barrier against any sort of environment that we're interacting with. This is just another example here. Chromium, even good stainless steels, still have multiple layers of oxides, not all of which are passivating, and not all of which are necessarily mechanically robust. So the way in which we find and create alloys that have good oxidation and corrosion resistance involves a complex combination of changing the alloy chemistry, the temperature at which it will be exposed or used. The original microstructure is important. The oxygen partial pressure we're exposing it to, and impurities, both in the metal itself as well as the environment. All of these will influence the chemistry, structure, density, continuity, and mechanical stability of the oxide scale, and that's what's critical for actually improving the passivation, preventing corrosion, fouling, or other sort of degradation mechanisms in these extreme environments. So again, we go back to our question of how do we understand this? How do we create a passivating scale on what would otherwise not form a good passivating scale? Now, in order to think about this, we turn to the literature, and we can see that in most cases we have some guidelines as to how to create and promote desirable protective oxides that would be useful in these situations. And the first thing that we think of is we would naturally increase the concentration of a favorable oxygen-active solutes. Like chromium, we put chromium into stainless steel, we improve the corrosion resistance, right? Aluminum is also a highly desirable oxide former because it's mechanically robust. And aluminum is a little bit more finicky though. But the consequence of adding these solutes is not only that you increase the cost of the alloy, but you also may change other properties like the mechanical properties. Adding aluminum in excess to many iron and nickel-based alloys actually significantly reduces the strength. So we have to be very careful about this particular strategy. Another strategy that we see in some niche sort of applications is we just slow down the rate of oxidation. So we might have a low alloy meaning we don't have a lot of these solutes, but if we slow the process down, we can allow sufficient time for these favorable solutes to actually get to the oxidation front and form the oxide that we want. And then the third is a little bit less common, but we can also just take an alloy that has a low concentration of these oxidizing solutes and accelerate the diffusion of those solutes to the surface. Okay, so these are the three strategies that we have at our disposal, and we want to do this without compromising other properties. And so the first thing is to just demonstrate to you that if we increase the concentration of favorable oxygen-active solutes, this is all known. I'm just kind of laying a baseline for us. So we're going to look at this ternary phase space here, and then we're going to superimpose on this ternary phase space. In this case, I've moved away from the iron-based systems to work with nickel, just as a model system. So there's similar behaviors for iron-based systems as well. But in this particular case, I'm overlaying the expected oxidation behavior on top of the phase space. So we can see that if we have mostly nickel and there's not a lot of chromium or aluminum, we expect to form a nickel oxide and get internal oxidation, and this would not be desirable. If we increase both the aluminum and chromium concentration, depending on how we do that ratio, we would start to form a chromium oxide, and maybe a little bit of internal oxidation as well, because we have that layered or stratified structure of the oxide. But if we dump enough aluminum in, we will get a desirable aluminum oxide scale, with the caveat that we've oxidized it at the right temperature. So this is known, and I can show you, we're going to use this model system quite a lot, so I want to just demonstrate that this model system, which we use sputter deposited thin films, represents what we already know. Okay, so we know this, but I want to show you that by working with these little tiny thin films that we can replicate what we know, that they are in fact representative. So I'm showing you here, actually this is TGA data, or thermogravimetric analysis data, when I'm plotting time versus the mass change. So the slower the mass change, the better the oxidation resistance. So in this particular case, I have a nickel-chromium composition, and I'm going to oxidize it in here under nitrogen. So it's not really purified nitrogen, but so there's a little bit of oxygen in there, and so we can see that as we heat it up to 900 C, the mass changes, and we generate a microstructure that looks like this. So this is my original metal film, and I have a nice, dense, continuous oxide forming on top. The chemistry hasn't changed. There's no aluminum in here to form aluminum oxide, so that's fine. If I take the exact same film and do the exact same experiment now in air, I also form a chromium oxide scale on my thin film, which is now right here in the middle. And this dark region that's oxide in both cases, you can ignore the contrast at the bottom here. That's just an artifact of the sample preparation. But now the oxide, you can see this mass gain is huge, but it doesn't actually look like there's as much oxide here because it has this spiky-like morphology, which means it's more prone to fall off or delaminate with time. So it's mechanically compromised, and because of the spiky morphology, it's less dense. There are easy access pathways to the surface, okay? And this is just a matter of the relative rate of oxidation, right? And so we talked about that was our second strategy. So the first strategy is change the chemistry. The second strategy here is to change the rate of oxidation. And so we can see that here. So we actually heated at the same temperature, the same rates, but we changed the partial pressure in our environment, and we got vastly different outcomes. Again, we kind of know this. This is used in a number of applications. Now the third one is to accelerate the diffusion, and this is one that is not as commonly explored. And here is actually we're working with the sputter-deposited thin films. Is actually quite interesting. So we know there's not a lot of ways that we can accelerate diffusion. Diffusion is a function of time and the chemistry and the lattice of the material itself. But there are things like grain boundaries that dramatically increase and accelerate the diffusion in a material. So the question is, if I take an alloy, a coarse-grained nickel-chrome alloy like this, versus a sputter-deposited thin film with a nanocrystalline structure of the same chemistry, do these oxidize the same way at all? The question is, no, they don't. In fact, we have shown in the literature, empirically at least, that if I take the same oxide map that I showed you before, that chemistry influences the type of oxide we get, and I change the grain size by an order of magnitude, I shift that whole favorable aluminum oxide region down to much lower aluminum concentrations. So even though I don't have as much aluminum in my system, because I have these fast diffusion pathways along my grain boundaries, and because I now have a plethora of nucleation sites, I can grow and develop a desirable oxide scale much faster, and it becomes protective even though I haven't changed the chemistry. Okay, so we've seen this empirically. Now we need to understand a little bit better actually why this is happening. So what we did, and what my student Parlov did, is he went and he took 3 different compositions here in this oxidation space here, expecting that they each behave a little bit differently. So these are the compositions that we're working with, and we'll try and keep that color scheme consistent. And so here, what I'm showing you is that just kind of confirming that empirical trend that we saw before, that this is the high enough aluminum concentration that it should in fact form an aluminum scale. And you can see that this, sorry, I didn't put this on here, but the blue is the aluminum in our EDS maps, and so we have in fact formed an alumina scale rather than a chromia scale. And if I were to show you the full EDS map, there is no chromia scale. It is just an alumina scale. The chromia stays, or the chromium metal stays in the alloy. And that's what we would expect. Now, if we go to a lower aluminum concentration, again, for a coarse-grained alloy, we would expect that this would form a chromia scale. But because we have a nanograin structure to start with, the lower aluminum concentration is sufficient, again, to make an aluminum oxide. Now, many of you are familiar with oxidation behavior, especially in the area of aluminas, know that alumina comes in many forms. It can be amorphous, it can have a wide range of polymorphs, again, not all of which are equal. But the interesting thing about this low aluminum containing oxide scale is not only is it aluminum oxide, it is the desired equilibrium alpha phase. And we can see that by this photostimulated luminescent spectroscopy over here. The purple one here is a reference of actual sapphire. And for both the low aluminum and the high aluminum, we have this characteristic doublet that is not seen in any of the other sorts of polymorphs. So this was actually quite surprising because typically we expected to get aluminum oxide here, but not at the temperatures that we went to. We only went to 900 C. Oftentimes, we only find the alpha phase of alumina forming above 1,000 degrees C. All right, but the alpha alumina phase is actually the one that is protective. So when we go back and think about the application we started in, this is the one that we actually want to form, not any of the other ones. Okay, so we've demonstrated that this chemistry effect does in fact work. We were surprised by the formation of this continuous alpha alumina phase. But if you're paying close attention here, and you look at our micrographs that we have over here on the left-hand side, the microstructure of the thin film looks a little bit different. The contrast that you're seeing here, this line is the only grain boundary that you can see in this field of view, because the microstructure has coarsened so rapidly over this 1 hour at 900 degrees C that's effectively become a bamboo-like structure where the size of the grains is the full thickness of the film. And so these are now micron-sized grains. They're not nanocrystalline anymore. So if they're not nanocrystalline, then how much is this whole nanocrystalline idea really impacting the oxidation behavior? And here's a little bit closer inspection. So the previous slide was after a whole hour. This is the as-deposited microstructure I showed you before. If we oxidize it for 5 minutes, only 5 minutes. And it's a real 5 minutes. We didn't ramp up, and it took an hour to ramp up. We preheated the furnace, we inserted the specimen for exactly 5 minutes, and then we pulled it out and quenched it, right? So this is, and because it's a very small sample volume, quenching is actually realistic here. The grain microstructure is fully equiaxed here. There's no evidence of this columnar nanocrystalline structure anymore. If we go for a full 15 minutes, we've already established this coarse-grained bamboo-like structure in our thin films. So really, how much can this nanocrystalline idea actually be playing a role? It must be doing something because we can see the evidence. But is it really the nanocrystalline behavior? So what we did, and we did this for other reasons, but it had unique consequences. And I'm going to apologize for a second because it's very warm in here. I'm going to take my jacket off. Okay. So what we did is we introduced to these same alloys, the nickel, chromium, aluminum system, we introduced a known reactive element, which is yttrium. And yttrium provides, in this introduction, we only introduced about 1% or less of yttrium. And then we put it back through the same rigor of tests that we had before. So this is the same data I showed you earlier with the spiky oxide that was forming. This is just nickel chrome. If I add aluminum to the same ratio of nickel and chromium, I have a lower slope and a lower point here on this plot, which suggests it has better oxidation resistance. That makes sense with the rules that we laid out. Higher aluminum concentration, lower oxidation resistance, or higher oxidation resistance. Now, if I add yttrium to both of these thin films, both of the curves actually drop significantly. All right? So not just the one with aluminum, now both of them, even the one with just chromium, the oxidation resistance is much better. And so we're going to look at the microstructure over here of the high aluminum concentration with yttrium that's been oxidized in air. So we didn't take any efforts to oxidize it slowly. This is done in air. And the really dark gray down here, that's the original alloy film. If you could see the contrast a little better, and maybe those of you on the webinar actually can see the contrast better, the grains are equiaxed, so we don't have the columnar structure anymore. And this lighter region up here, that is the oxide scale. It's very dense, it's nice and continuous. And I'm going to overlay some EDS maps on top of this to give you a feel for what's happening during this process. The first one I'm going to overlay is the yttrium EDS map. Now, as we started, the initial thin films were chemically homogeneous to within our abilities to quantify the chemical homogeneity. There was no chlorine, there was no internal oxidation. And you can see that that's obviously changed. These little yellow clusters were not there before. These are all little yellow yttrium clusters. There's also yttrium incorporated into the oxide scale. That's actually what we had expected. The literature tells us that these reactive elements should go into the oxide scale. But this whole bit of clustering down here was rather puzzling to us. So we were worried that we had some internal oxidation. Yttrium has a high affinity for oxygen. Perhaps we're just forming little oxides. But we don't see any evidence of that either. You can see here that the oxygen, to within the ability of quantifying oxygen via EDS, we don't see any significant oxygen uptake in the alloy itself, just in the film. Now I will argue this is most definitely aluminum oxide. I'm not going to show you those chemical maps because I really want to focus on the role of yttrium here. Now, this is all quite interesting, but we really wanted to understand what was going on with these little yttrium clusters. And so we went back and we did some shorter oxidation steps. And so this is just the nickel chrome, no aluminum here, but even after 15 minutes, the interesting thing is, rather than forming these big bamboo-like structures where the grains are all the way through, after 15 minutes of oxidation, some of this columnar structure actually is still retained. All right? And we again see these little nanoclusters. The nanoclusters form on the top and bottom of our thin film, but they're not found in the center of the film. And we're also nucleating the oxides, right? This is a nodular-based oxidation mechanism. Without the yttrium, I think I'll show you later, it's also oxidizing, but it is very focused on the surface, and we don't see this sort of nodular growth. And so it's quite interesting because we expected to see a continuous oxide scale here, but that's not what we're seeing necessarily. So the mechanism of oxidation is also a bit different. So we have these nanoclusters and we have oxidation even after 15 minutes, and we preserve some of the nanostructure. So again, we needed to have a better understanding of, presumably, these nanoclusters of yttrium are doing something to change the diffusion of the oxidizing species to the surface, the aluminum to the surface. But we didn't understand why, necessarily. So we took out the idea of the oxygen driving force. And we just did microstructure evolution. We just wanted to know what these same chemistries would do with and without yttrium if there was no driving force for oxidation. And so what I'm showing you here is on the top row is a nickel chrome aluminum alloy, and on the bottom is a nickel chrome aluminum yttrium alloy, right? Otherwise, the chemistry is the same as the bottom row has yttrium, and then we have these different time steps. So we see that we start, and these are at 100 C already, but the as deposited structures are quite similar. Columnar, microstructure. We're not going to talk about these planar faults just yet, but all these striations, that's also a different interesting feature. But they're about the same grain size to start with. By the time we get to 650 C, there's no evidence of this columnar microstructure. We have relatively equiax grains already showing up. And you can see some of this is more obvious in the diffraction pattern, because down here in the yttrium-containing alloys, there's still ring patterns, which suggests that the grain size is very fine still. As we go to slightly higher temperatures, now, even in the yttrium case, we've started to create these equiax structures, and the grains are growing. And by the time we get to 900 C, the alloys without yttrium are very coarse. And we have fully equiax structures at 900 C down here with yttrium, but they're much smaller. Okay? So even without oxidation, even without that driving force, the yttrium is still playing a significant role in the way the microstructure is changing, which gives us some hint as to how the microstructure is influencing the oxidation behavior too. Now, what we can see here is we go back and we put the oxidation back in. So the yttrium, what I didn't show you is in the case of the, in this particular case, the bottom one where we have this evolution, we again see these yttrium nanoclusters, except now they're distributed all the way through the thin film. There's not this denuded zone in the center because we don't have the driving force for oxidation. But to come back to this idea of oxidation behavior, and really tie this story together about how we can actually manipulate oxygen scale formation by playing with a microstructure, we look at the comparison here, wherein for the yttrium-free thin films, at 15 minutes we don't have the microstructure we started with. We have the oxide that is along the top, it's still discontinuous. And if we go to the full 60 minutes, we get this pointy, not low-density oxide scale. Down here, by containing and using the yttrium, we preserve effectively the columnar structure just long enough to manipulate the early transient stages of oxidation to nucleate these oxides, and then those oxides are what dominate the rest of the oxidation behavior. It's all about what we establish within the first 15 minutes. This first 15 minutes is all that it takes to maintain that nanocrystalline structure, because after that, the behavior in the long term, whether we have a porous, non-dense coating or scale versus a dense, continuous scale, depends on the first 15 minutes or so of this oxidation behavior. Okay, so while the yttrium and the microstructure are changing rapidly, there is something in this transient stage of oxidation that is quite critical to the overall oxidation behavior and then the longevity of the component in oxidizing environments in general. So we think that there's actually quite a lot here in terms of understanding and using the microstructure, even if we don't keep it long term, to improve the durability and the oxidation resistance of service components. Now, I did also mention that this idea of grain boundary diffusion, we preserve the grain boundaries long enough, we get better oxidation resistance. But grain boundary diffusion isn't limited just to surface effects. We saw this when we took the oxygen out of the system and just looked at the microstructure evolution. There are still interesting things happening there. And so we want to kind of think about, well, where else would this accelerated diffusion be interesting or useful? And we can think about this in the context of phase transformations. So first thing we need to do is actually quantify this accelerated diffusion. And what we've done here is start making these nano or micro diffusion couples. In this particular case, I've got a layer of nickel on top of a layer of chromium, which is interesting for a lot of other reasons that I don't have time to talk about today. But then we can actually perform a traditional diffusion experiment where we have the nickel diffusing into the chromium and the chromium diffusing into the nickel, and we get these nice interdiffusion profiles. We can use a very traditional Boltzmann-Matano sort of approach to deconvolute this data and extract the actual diffusivity. In this particular case, I'm showing you that the diffusivity of nickel into chromium is on the order of 10 to the minus 13 meters squared per second. Which, if you look at some of the literature for something like nickel going into a BCC metal like chromium along grain boundaries, is actually pretty reasonable until you pay close attention and realize that we did this at 600 degrees Celsius, when diffusion should be slow, very slow. All right, and so clearly we have some interesting things happening here. I don't have time to get into the details of this, but actually if we go a little bit longer than 30 minutes here, we actually start to see the development of the nickel-2 chromium intermetallic phase, which should take hundreds of hours to start to form. Okay? So now we can actually utilize and capitalize on these fast diffusion pathways to study things like sluggish diffusion or sluggish phase transformations that otherwise we don't have the patience necessarily to study in depth, but are really critical to certain applications like a nuclear reactor that's operating for 80 years around 300 degrees Celsius. We can't actually validate that for 80 years. So it can be very difficult to predict what's happening after such a long time period unless you're actually pulling components out of the reactor. So we're going to think about this. Like I said, we have these grain boundaries which are accelerating diffusion. We have some other defects in these microstructures as well, and we need to pay attention to those as well. There are these grain boundaries, there are high density of vacancies, but there are also these planar faults. And so you can see those here. In this particular micrograph, the black arrow indicates the direction of growth of this microstructure. And the white arrows are just trying to point to some of these planar defects that we think are interesting. You can see down here in B, the contrast is a little bit higher resolution. You can see the contrast of some of these planar faults. They're very systematic. They're very well organized. The texture of these films is quite high. And there's consequences for this. In fact, what was really surprising to us is that this is a nickel-based alloy here, but it's not all face-centered cubic in its structure. Because of the high density of these planar defects, it's actually about 50% HCP, or hexagonal close packing. You can see that from the high-resolution image down here. Rather than just having a single plane that's affected by a twin or stacking fault, we actually have large regions that are impacted by this, and that's manifested in its diffraction pattern as well. And so I think I want to come back to this because there's more complexity here than I'm giving it justice, but I don't necessarily have time to get into it. But basically what I want to show to you is that by using these planar defects, we can look at these sorts of sluggish phase transformations that are quite interesting. So what I'm showing you here, this is for a nickel moly chrome alloy. It's used commonly as a ring alloys in gas turbines. It's used in the nuclear industry. And this is the TTT diagram for that. Hopefully we all at least seen something like this before. The TTT stands for time, temperature, and transformation. And basically this tells us that for this particular alloy system, which is precipitation strengthened, so we actually want other phases. It's a two-phase alloy. It should be a two-phase alloy. That second phase isn't necessarily the equilibrium phase. The second phase that we want is actually this one right here, which is a metastable precipitate that has a structure of nickel-2 molychrome like this. And if we want to get that, we take our alloy, we anneal it, and then we do a heat treatment down here for about 24 to 72 hours around 650 C, and we just cross this line and start to develop this precipitate structure, which has implications for the strengthening mechanisms and so on and so forth. Now, if we leave this in service for a very, very long time, or we are just trying to study it, and we extend this at the same temperature, we get out to hundreds of thousands of hours before ultimately we get down here to the equilibrium structure. And so you can see that there are many steps in between here. necessary to finally get here. And if you actually do start to see this equilibrium structure in your microstructure, it's a bad thing. The mechanical properties have suffered. This would be considered overaged. But you want to know when that's going to happen, and so you need to understand all these bits in the middle to make sure that it hasn't started to happen in your alloy in service. Okay, so what we did, we know that this is well known for commercial alloys, coarse-grained alloys that have been properly processed. And so we applied the exact same heat treatment to our thin films of the same sort of chemistry. So we did this 48-hour heat treatment at 650 C, and we did not get what we expected. So what I'm showing you here in this X-ray data, over here is the as-deposited X-ray data, and here is our annealed X-ray data. And so here we see that we have, if we actually do a quantitative fit, like I said, we have about 50% of this HCP phase and about 50% of the expected FCC lattice. When we do the annealing, what we expect is this phase up here in the dashed line. Rather, we get what I'm labeling here as the DOA phase, which is that equilibrium structure. And we had to corroborate this by a couple different means because it's actually not directly obvious from the TEM, but this DOA phase is rarely reported in the literature, largely because it takes so long to form, and because of this bit here, that even if you give it time, you still require some mechanical deformation to assist this shear transformation. But because we already have such a high density of HCP-like stacking in our microstructure, we've actually just skipped all of these steps, and we can actually study the implications of what this precipitate actually does to our microstructure by direct precipitation. And to ensure, and so 48 hours, fine, we know the diffusion kinetics are accelerated, perhaps 48 hours is too long. We went back and did some in situ treatments. Perhaps we just smashed all of those different steps into 48 hours, and we didn't see them because we started with such a long heat treatment. Well, we did in situ heat treatments, and we actually found none of that evidence. Trust me, based on the analysis here, or you can look very closely, that all the reflections that we see and the transfer of intensity between the sublattice reflections are associated only with the equilibrium DOA phase rather than the expected nickel-2 moly phase, which is the metastable precipitate. Okay, so this is all well and good. It's quite interesting. But maybe I just changed everything when I sputter deposited this film, right? So as a sanity check, what we did is we actually did an anneal on the microstructure. So we took the thin film, that columnar thin film, and we heated it up to 1066C, which is the industrial spec for this particular alloy. For 30 minutes, we quenched it, and we got rid of the nanotwins. We got rid of the texture. And in fact, when we quenched it, we start to see this short-range ordering, evidenced by these diffuse scattering by these little arrows here. This is a precursor. This is the first step in the transformation to the metastable phase. If we then do the aging at 48 hours at 650 C after the quench, we get back to exactly where we expect we ought to be. The little wavy lines in this microstructure are the platinum-2 moly precipitates, the metastable ones that we didn't see before. Right? So we can actually recover the original phase evolution pathways by annealing the planar defects away. So now we have the ability to turn this on and off in a small volume sample that we can rapidly make in our labs. Okay, so with that in mind, I'm going to wrap up here because I think my time is running short. But I just want to emphasize from this last bit to show that nanocrystalline thin films do in fact provide a unique opportunity to accelerate traditional physical metallurgy, study things like oxidation behavior and complex phase transformations that otherwise require a large volume of equipment and quite a lot of time and investment in order to understand. So there's some flexibility here that we've gained by exploring these thin film materials. Okay, so let's tie this all back in together. We had kind of three different segments of this particular talk. We started with an actual very applied and industrial space where we were looking at mitigating carbonaceous deposits on pipe steels by using a surface passivation to prevent the corrosion that is correlated with these carbonaceous deposits. We then spent a lot of time talking about how we actually form and control such an oxide on real materials by using these model thin film specimens. And so we could show that the transient stages of oxidation, if we can control those, we can control the ultimate oxidation resistance of an alloy without sacrificing the chemistry. And then finally, we just had this little bit at the end where we talked about how these unique nanocrystalline structures might be useful for other things as well, including understanding sluggish or complex phase transformations that are also of interest to these sorts of extreme environments. So with that, again, I should acknowledge all of the support and the many people who helped with this particular work, including BP-ICAM. Some of this work was supported by the Department of Material Science and Engineering, as well as the Royal Academy of Engineering, who supported my particular visit here, all of my students and collaborators. And if nothing else, I'd just like to wish all of you a very happy 4th of July, especially for those of us listening from the US. All right, and with that, I'm happy to take